Last lecture we had discussing about the perspective transformations, and there we had defined the perspective transformation matrix, and given a point in three-dimensional space, that is to say in the world coordinate, we knew how to compute the coordinates for the camera. So what we had was a relationship of this nature, where we had the world coordinates represented in terms of this column vector WH, where basically this WH was represented in homogeneous coordinates. That's to say that instead of the three coordinates x, y, z, we had a fourth element also in the column vector, and then we were dividing the first three elements of the column vector by the fourth element in order to get the world coordinates as such. And then actually the transformation matrix was P, and we were multiplying this transformation matrix with WH column vector in order to get CH as the transformed column vector, again in the homogeneous coordinates, from which we could compute the x and the y coordinates for the image point. For a given point in the 3D space, that is to say in the world coordinates, we were finding the coordinates of the image point, coordinates of the corresponding image point. Now what we are going to do is a reverse process. In fact, that is the problem which I introduced in the last class. That is to say, if the image point is given to us, that is to say CH is known to us, then how to recover the point in the three-dimensional space, that is to say how to recover WH given CH. So all that we have to do is to apply the inverse transformation matrix, which was P inverse, okay, where P inverse was defined in this manner, and we had assumed the CH to be consisting of these elements kx0, ky0. The z component we were taking as 0 because the image plane was rotated, the image plane was located at z equal to 0, and then the fourth element was k, so that we get straight away x0 and y0 as the coordinates of the image point, okay, in terms of the camera coordinates. Now the question is that if we take this point CH, okay, and apply the inverse transformation, can you tell me what results for WH? Has anybody worked out? Yes. Beautiful. Somebody has given the reply. Actually we are getting the image point as CH was our given image point, kx0, ky0, 0 and k. This was our image point, and by applying this relationship WH equal to P inverse CH, we are getting WH as kx0, ky0, 0 and k. So that means to say that what is the what is the object point, or rather what is the actual point for which we are taking the image, what is the coordinate of that in the 3D Cartesian coordinate space? It is simply x0, y0, 0. This is the three-dimensional coordinate for the object point, for which we had got the image point at x0, y0. So that means to say that the object point is getting located at the image point itself. But do you think what you have got is correct or not? Look, we had the point, we had the image point at x0, y0, and we are recovering the corresponding three-dimensional object point. and we are getting the same coordinate x0, y0, 0 as the object point in the three-dimensional space. Is it that this relationship is correct? Is it what you what you got is correct, or there is a catch? All right. Now let us see one thing. Let us go back to our original imaging diagram which we had in the last class. You see, P was the object point having coordinates capital X, capital Y, capital Z, and we had Pi as the corresponding image point having coordinates x, y. Now the problem is that we have got this xy, somebody has supplied this xy point to us and we are trying to recover P, but rather than recovering P, we are getting the same point as Pi as P. Okay, so that means to say we are unable to recover P fully. And why? What is the reason? I think the reason is quite simple, because you see this ray PO, okay, and if you are extending this ray, then it intersects the imaging plane at this point Pi. So that's how Pi happens to be the image point. Now the line PIO, if I join, okay, that is to say the ray PIO, if I consider the ray from Pi to O, okay, and extend this ray, then the actual object point may lie anywhere on this ray, and still we are going to get the same point Pi as the image point. Is that clear? So that means to say that from the object point to the image point, it is not one-to-one mapping. It is a many-to-one mapping in the case of object point to image point. Okay, take any point on this ray and the image of that is Pi. So that means to say that if somebody gives me Pi, okay, recovering P is not possible. Okay, we need to know some other information, and let us see what information do we need to know in order to determine this object point P. All right, you remember that we had a relationship like this, okay, which had defined the transformation from the world point xyz, capital XYZ, into the image point in camera coordinates small x and small y. Okay, now from this relation I can write down capital X becomes equal to, from this, if I call this as equation 1 and if I call this as equation 2, then from equation 1 I am getting capital X becomes equal to lambda minus z multiplied by x divided by lambda. Is that correct? And I am getting capital Y as lambda minus z into small y divided by lambda. Now if x, y are known to us, lambda is a parameter for the camera, that is to say the focal length. Now only if somebody tells me about this z, if somebody supplies the data pertaining to the z coordinate of the object point, then only we will be able to recover this capital X and capital Y. Okay, I think subjectively also it is not difficult to think that why this kind of a phenomenon has occurred, because after all we are taking the projection of a three-dimensional world space onto a two-dimensional plane. So obviously what we are missing is the information pertaining to z, and since the z information is lost, okay, that is the reason why we are unable to reconstruct or unable to get back the original object point from the image point. From a single view, it is not possible. We are considering only a single view, only one camera we are considering, and from that it is not possible for us to recover the three-dimensional point completely. If we would like to recover, either somebody has to supply the data pertaining to Z, or we have to do some other imaging arrangement. Maybe instead of one camera, we need two cameras, and that is exactly what is done in the case of stereo imaging. I am postponing the discussions on stereo imaging for some time, okay, but from this imaging geometry, it is quite clear to you that you cannot recover the original object point P from the image. Is that clear to all of you? Now, let us consider the camera model in a more general form. Now, the relationship 1 and 2 which we have got, okay, is of course a camera model, but it is a very simplified camera model. What was the basic assumption that we made in deriving this camera model? If you remember correctly, the basic assumption which we had made was that the capital XYZ coordinate system of the world and the small xyz coordinate system of the camera, they were assumed to be exactly identical, and the origin was assumed to be the same point. But let us now consider a general case where we are not considering the identical coordinate system. The coordinate system, we will take it differently. Now, this capital XYZ is the world coordinate system. This you already know. And now, let us assume that the camera is located somewhere at this point. Okay. And let us also think of some fixing arrangement for the camera. That means to say that we have a base like this, okay, and on this we are mounting the camera, and you are permitting the camera to move little bit. let us assume that the camera which is shown over here is mounted on a gimbal. This is the gimbal, and on that the camera is mounted, and we are assuming that the gimbal is located at a displacement which is given by the vector W0. So the W0 vector indicates the displacement of the camera's gimbal center from the capital XYZ coordinate system. So W0 is the displacement vector of the gimbal center. Now we are also assuming that with respect to the gimbal center, the camera's imaging plane is located at another displacement vector R0. So R0, the displacement vector R0 indicates the displacement of imaging plane with respect to the gimbal center. And the camera has been given some freedom, that is to say, you can move the camera like this or like this. That is to say, the camera has a freedom movement in the three-dimensional space. So there can be a pan and there can be a tilt for the camera. So we are assuming that alpha is the tilt angle, and this tilt angle is actually defined with respect to the z-axis. The tilt angle is defined with respect to the z-axis, and the pan is defined, the pan is given by the angle theta is defined with respect to the pan, and this is defined with respect to the x-axis. And then we are assuming that there is a point in the world space which is given by the vector W. So the W vector, as before, indicates the world point, that is to say the object point, and we are taking image of this point W onto the imaging plane which is shown over here. This is the imaging plane, and on this we are taking the image of this point W. So it is quite simple. We have to join this point W with the focal point of the lens, and then we have to extend that ray, and the place where it intersects the imaging plane, that will give you the actual image point. So what we have to do, if we would now like to know the relationship between this world coordinate point given by this W vector, okay. So W vector indicates the world coordinate of the object point. So given this W, we now have to know that what is the camera coordinates, okay. We have to compute this CH vector, okay. If we can compute the CH vector, then we will be able to determine the x and y coordinates of the imaging point, correct? But in order to do that, we have to apply several transformations, because our earlier relationship which you had seen sometimes back, that is to say, I was talking of this relationship. This is defined only with respect to the same camera positions, the same position for the cameras XYZ and the world coordinates XYZ. But when the camera center is displaced, what we have to do? We have to apply a series of transformations. Okay? The transformations are, number one, that there is a displacement of the gimbal center. So, the first factor which we have to take into consideration is the displacement by an amount W0 vector. And then the second factor which we have to take into consideration is the pan and the tilt. So, pan, the third factor is the tilt, and then we have to consider the displacement vector R0. Now, if you apply all these transformations, okay, then what you are getting is then you are just aligning the camera's coordinates with the world coordinate, and after doing that alignment, you can apply the normal perspective projection equation, okay, which was that same expression which we had last time. That is to say that after aligning the camera coordinate with the world coordinate, we can apply this transformation. That is to say, the perspective transformation matrix P is to be multiplied with the column vector WH in order to get CH. So, these are the different steps which we have to perform. And now, let us consider all these four elements one by one. Now, the displacement W0, okay, and how can we indicate that? Its components, let us assume the components for this displacement vector to be x0, y0 and z0. So, this matrix indicates the displacement. So, that is the first factor. The second factor is the pan. The third factor is the tilt. Pan is by an angle theta and the tilt is by an angle alpha. Okay. So, pan of the x axis and tilt is of the z axis. Now, both these factors, pan and the tilt, can be combined together in the form of a concatenated matrix which is R theta R alpha. If you remember our discussion in the earlier class, okay, the question which is asked is that why are we getting minus x0, minus y0 and minus z0? Because I have assumed a displacement of x0, y0 and z0 in the positive direction. So, in order to bring the camera or in order to align the camera with the world coordinates, okay, I have to make a displacement minus x0, minus y0 and minus z0, okay, in order to align it with the world coordinates origin. Is that correct? Okay. Any other question?
So this theta and
yes. Theta which is the pan angle. Yes. What is your question?
What is it with respect to the figure which we do?
Okay. Right. Now look at this figure. Okay. This figure we had shown in the earlier class. This is our XYZ coordinate system, and we had defined this rotation theta with respect to Z axis. Now, I have said that the pan is for the X axis. So, if I want this x-axis to be rotated. If this is my z-axis, and if I want the x-axis to be rotated, I will give it a shift like this. So this is my angle theta. Okay, this is the angle theta which is above z, but whereby we are transforming the x-axis. We are moving, this is x-axis and this is z-axis, and we are just moving it like this, okay, by an angle theta. Okay. Now our r theta matrix was like this. Its elements were cos theta, sin theta, minus sin theta, cos theta, rest of the elements like that of the identity matrix, and our r alpha was like this. So combinedly, if we want to do the panning by an angle theta and tilting by an angle alpha, tilting is for the z-axis. So that means to say that there I am keeping the x-axis position like this, and I am just tilting the z-axis, okay, again by an amount alpha. Okay. So r alpha is the transformation matrix for that, and r theta, r alpha combinedly will give me the pan, the effect of pan as well as the tilt. So what do we get as r theta, r alpha? I am getting it like this. Its elements are cos theta, sin theta, 0, 0, minus sin theta, cos alpha, cos theta, cos alpha, sin alpha, 0, then sin theta, sin alpha, minus cos theta, sin alpha, cos alpha, 0, 0, 0, 0, 1. These are the elements of the concatenated r theta, r alpha matrix, which I am now calling as the matrix capital R. Okay. Okay. The elements of this R matrix are: first row cos theta, sin theta, 0, 0. The second row minus sin theta, cos alpha, cos theta, cos alpha, sin alpha, 0. The third row sin theta, sin alpha, minus cos theta, sin alpha, cos alpha, 0. The fourth row 0, 0, 0, 1. This is our R matrix, and then finally we have to displace the origin of the image plane, okay, by the vector R naught. So let us call that as the matrix C, okay, and the matrix C is the elements of matrix C are 1, 0, 0, minus R1. I am assuming R1, R2 and R3 to be the components of the R naught vector. R naught was the vector which had defined these three elements, R1, R2 and R3. So my combined the matrix C is, okay, indicating that displacement. It is 1, 0, 0 minus R1. R1 is the x component of the displacement. The second row is 0, 1, 0 minus R2, R2 being the y component of the displacement. The third row is 0, 0, 1 minus R3, R3 is the z component of the displacement. The fourth row is 0, 0, 0, 1. So this 4 by 4 matrix indicates the displacement of the imaging plane with respect to the gimbal center. Capital R indicates the pan and the tilt, and what we had earlier was not W0 rather, because W0 was the vector. W0 was defined as the vector x0, y0, z0. So we should write here as yet another matrix. Let's call that as G. So the matrix G was defined like this, which consists of the elements of this displacement vector W0. So G indicates the displacement of the gimbal center with respect to the world coordinate origin. R was like this, C was like this, and combinedly now we can write that the combined transformation matrix A now becomes C R G. Anything else?
Sir, in C matrix we have again taken minus R1, minus R2, minus R3 because of the reason that it is in the positive side.
Yes, in C matrix we have taken the elements to be minus R1, minus R2, minus R3. The reason is same as before. That means to say that we have to give a negative shift in R1, R2 and R3 directions. And we are getting the total transformation as C R G. Any other thing which I have left out? No, WH. Now finally my relationship has to be CH should be equal to AWH, where A is the transformation matrix. But is this correct? A equal to CRG? So on this I have to apply the perspective transformation. I have to apply the perspective transformation, and what was my perspective transformation matrix? That was P. So I must have the combined transformation matrix A as P, C, R, G. If I call that as A, then my CH will be equal to, CH vector will be equal to the A matrix product with the WH column vector. WH column vector indicating the world coordinate point, and if I know A, then I get CH. Is that clear to all of you? Now, if you are solving for this, means if you, since I have already given you the composition of this G matrix, R matrix, C matrix, and you also know the composition of this transformation matrix P, okay, you can compute the elements of this A matrix, and if you multiply this by the world coordinate column vector WH, then by solving you will get the relation for X and Y, and I am giving you the result directly. The small x for the image point, the small x is equal to lambda times x minus x0 cos theta plus y minus y0 sin theta minus r1, this divided by minus x minus x0 sin theta sin alpha plus y minus y0 cos theta sin alpha plus r3 plus lambda. Okay, so this is the expression for x. I repeat, x is equal to lambda times x minus x0 cos theta plus y minus y0 sin theta minus r1 divided by minus x minus x0 sin theta sin alpha plus y minus y0 cos theta sin alpha plus r3 plus lambda. So that means to say that if somebody gives me the angle of the pen, the angle of the tilt, that is alpha, if somebody tells me the displacement of the gimbal center with respect to the coordinate system, that is to say x0, y0, if they are known to us, okay. Well, I have omitted one term over here, so please note down. This was minus x minus x0 sin theta sin alpha plus y minus y0 cos theta sin alpha minus I have omitted one term, I am writing it down, minus z naught cos alpha. So it is consisting, the denominator consists of 1, 2, 3, 4, 5 terms, and the third term is minus z naught cos alpha. Okay. So if theta is known, alpha is known, x naught, y naught are known, lambda is constant for a particular camera, r1, that is to say the amount of displacement in x direction, and the amount of displacement in the z direction, r3, if these are known to us, then we get x. Okay. And very similarly, we obtain y as follows. The numerator is y is equal to lambda times, the numerator is minus x naught sin theta cos alpha plus y naught cos theta cos alpha plus z naught sin alpha minus r2. The denominator is minus x naught sin theta sin alpha plus y naught cos theta sin alpha minus z naught cos alpha plus r3 plus lambda. Okay. So this is the way we can recover the, we can compute the camera's xy position, or rather the xy position for the image point for a given point in the world coordinates. Now that means to say that we must know all these parameters fully, that is to say the composition of this C matrix, R matrix and G matrix, everything should be known to us if we want to compute the image point. But what happens if it is not known to you? If these are unknowns, is there any way by which you think you can compute the image point? Well, if I give you a known object, for which the capital XYZ, that is to say the world coordinate components are known, and for those points the corresponding image point is also known to you. If I give you for certain number of points, I give you the world coordinate point and the corresponding camera coordinate point. Do you think that it is possible for you to get the composition of this combined transformation matrix A? Let us see whether we can do that or not. So we are assuming this combined transformation matrix A to be P, C, R, G. Okay, and we have CH column vector equal to A matrix product with the WH column vector. Now letting K is equal to 1 in the homogeneous coordinate system. We can write CH1, CH2, CH3, CH4, where CH1, CH2, CH3 and CH4 indicates what? The homogeneous coordinate component. That means to say the X will be CH1 divided by CH4. The first element divided by fourth element will give me the X component. CH2 by CH4 will give me the Y component. CH3 by CH4 will give me the Z component. Of course, I am interested here in solving for only the X and Y components. So it is CH1 by CH4. The second is CH2 by CH4. And this should be equal to the A matrix. So the A matrix elements I am writing in this form: A11, A12, A13, A14, A21, A22, A23, A24. The third row: A31, A32, A33, A34, and the fourth row: A41, A42, A43 and A44. So this is my transformation matrix A, which is unknown. So I have to compute the elements of this transformation matrix if certain number of points are given to us, and this should be multiplied by the column vector, okay, indicating the x, y, z coordinates, and I have assumed the value of k to be 1. So what will be the elements of this vector? Capital X, capital Y, capital Z, and the fourth element 1. So this is the relationship CH equal to AWH, which I have just written it in this fashion, and I shall also make use of these relations, that my X coordinate in the image will be CH1 by CH4 and Y should be equal to CH2 by CH4. Alright. Now if I have that, okay, that means to say in place of CH1, if I substitute X times CH4, so we have here CH1 should be X times CH4 and CH2 should be equal to Y times CH4, correct? And by writing it that way and by expanding this, we get X CH4 equals A11X plus A12Y plus A13Z plus A14. YCH4 we are getting as A21X plus A22Y plus A23Z plus A24. Okay, this is the X CH4 and Y CH4, that is to say this CH1 and CH2, which I simply get by multiplication: A11X, A12Y, A13Z, A14. CH2 is A21X, A22Y, A23Z and A24. And again from this matrix for CH4 I should get CH4 equal to A41X plus A42Y plus A43Z plus A44. So CH4 should be equal to A41X plus A42Y plus A43Z plus A44. And if I substitute this CH4, this value of CH4 in these two equations, in the top equation number 1 and equation number 2, if I substitute this expression for CH4, okay, what we get is like this. we get A11x plus A12y plus A13z minus A41x capital X minus A42x capital Y minus A43x capital Z minus A44x plus A14 equal to 0. Let us call this as equation number 3, and then we also get A21x plus A22y plus A23z minus A41yx minus A42y capital Y minus A43 small y capital Z minus A44 small y plus A24 equal to 0. This is equation 4. Now, in these two equations 3 and 4, okay, you see what is given to us? Capital X, capital Y and capital Z, they are given to us, okay, and we have to compute small x and small y. These are to be computed, and now in this equation A11, A12, A13, A41, A42, A43, A44, all these things are unknown to us. Now, if somebody gives me certain number of points for which capital X, Y, Z is known and their corresponding x, small x and small y are known, then you can think of solving for this A11, A12, all these elements of the A matrix. But for one point, if I supply you one such point given the capital X, Y, Z and the corresponding small x, y, you get two equations. And how many unknowns? I am marking all the unknowns in this equation. A11 is unknown, second unknown, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th, 11th, 12th. There are 12 unknowns, and if I want to solve for 12 unknowns, okay, 12 unknown elements, okay, then how many equations do I need to have? I need to have 12 such equations, and 12 such equation means each known point is giving me two equations. So that means to say that I must have 6 known points. So if for 6 points, okay, I know that for the world coordinates x, y, z, what is my small x, small y in the image space, okay. If somebody supplies me this information for 6 known points, okay, then I will get 12 equations, and I have got 12 unknowns, so I can solve the equations, the system of linear equations, and then the entire composition of the A matrix will be known to us. And if A matrix is known to us, then given any world coordinate point, okay, we can get the corresponding image coordinates. If A can be computed fully, if I give you WH, then you can compute CH. Any doubts?
We do not know A31, A32 of this A matrix.
A31, A32 of this matrix. Okay. Now, really speaking, you need not know this A31, A32, A33, A34. I tell you what, that will only tell you about this CH3, and you are not really bothered about this CH3 because you are only finding out the x and the y components of this column vector. Okay, the z component of the column vector is of no use to you because you are only taking the image on a plane, on an xy plane. So ch1 and ch2, and for that knowing these many components should be sufficient for you. Any questions? So this procedure, that means to say that for 6 known points, okay, if the xyz is known, that is to say the world coordinate point and the camera coordinate point xy, the corresponding camera coordinate point xy are known to us for 6 such given points, then you are doing a kind of camera calibration with respect to these 6 points. You are doing a camera calibration and determining the elements of this transformation matrix in order to get a proper transformation relationship between the world coordinate point and the image point. So this procedure which I have just now said is called as the camera calibration. Alright. Now with this we conclude our discussions about the imaging geometry. So now how from the 3-dimensional space an image is formed, okay, is known to us, and given the world coordinate points, how to get the corresponding image coordinates, that is also known to us. Now regarding this aspects of imaging geometry, is there any question? Alright, so we will proceed to our next topic, which will be on the low level image processing.